A very good day to our lecturer, Professor Madya, Engineer Technologist Dr. Muhammad Azahari bin Razali, and to everyone watching. We are from Group A1, and today we are excited to present our Thermodynamic 2 group project. Our topic focuses on the design and performance optimization of an advanced vapor compression refrigeration system incorporating two-stage compression, intercooling, and subcooling. Before we dive into the details, let us introduce our team members. Here are our team members. Our group consists of 5 members and we will taking turns presenting different sections of this presentation. To begin with, let's look at the introduction and background of our project. Assalamualaikum and hi to everyone. I Ahmad Daniel bin Muhammad Nasir, metric number AD2110209, and will presenting the introduction of our project, which is the design and performance optimization of an advanced vapor compression refrigeration system. Vapor compression refrigeration systems are widely used in industrial and commercial cooling application. However, conventional single-stage systems often have lower energy efficiency due to higher compressor work, resulting in a lower coefficient of performance or COP. Therefore, this project proposes the use of multi-stage compression, intercooling, and subcooling to improve system efficiency, reduce energy consumption, and achieve a higher COP. So we will continue to the literature review and related theory. Based on refrigeration theory and previous studies, several methods can be used to improve the performance of vapor compression refrigeration systems. Multi-stage compressions help reduce compressor work by dividing the compression process into stages. Intercooling lowers the refrigerant temperature between compression stages, while subcooling increases the refrigeration effect before expansion. The performance of the system is evaluated using the coefficient of performance, or COP, which is the ratio of refrigeration effect to compressor work input. In general, a higher COP indicates a more efficient refrigeration system. Therefore, these technologies are expected to improve the overall performance of the proposed system.
Good morning to Dr. Azahari and Andrew FANG. In this project, we built up a flowchart to visualize the continuity of the refrigerant cycle, ensuring that the mass and energy flow paths. The flowchart defines the pressure, temperature, and phase boundary at the junction of each machine. The refrigeration system begins with low-pressure vapor from the evaporator entering the low-pressure compressor, where it is compressed to an intermediate pressure. The discharged vapor is cooled in an intercooler, reducing its specific volume and lowering the work required for subsequent compression. The vapor then entering the high-pressure compressor, where it is further compressed into the condenser pressure and condensed into a high-pressure saturated liquid. This liquid undergoes additional cooling in a subcooler, significantly reducing its enthalpy and enhancing cooling capacity. The subcooled liquid is stored in a receiver before expanding through a valve into a flush tank, forming a two-phase mixture. Efficient phase separation ensures the minimal flash gas. The liquid streams drive an ejector, creating a low-pressure region that enters evaporator vapor. Through entrainment, mixing, and pressure recovery, the ejector pre-compressed vapor and recovers expansion energy, reducing compression workload and improving overall system COP.
Now we move to this slide. So this slide shows the main component selected for our advanced refrigeration system designs. This component were chosen to improve the energy efficiency and increase the coefficient of performance of the refrigerant system. So for the compression process, we selected the variable speed scroll compressor for the low pressure and the high pressure stage. This compressor offers high efficient, low energy consumption and reduced vibration compared to the conventional compressor. So the system also uses a microchannel condenser, which provides better heat transfer performance and more efficient heat ejection to the surrounding. Next, to enhance the subcooling process, a plate heat exchanger is used. The component lowers the refrigerant temperature before the expansion, increasing the refrigerant effect and improving overall system efficiency. Next is a flash tank separator is included to separate liquid and vapor refrigerant at the intermediate pressure. This helps reduce the compressor workload and improve the cycle performance. In addition, a refrigerant injector is used to recover the pressure energy that would normally be lost during the expansion process. This reduces compressor power consumption and further improve of the system COP or coefficient of performance. Next, This slide shows the remaining of the key component in our refrigerant system, which is electronic expansion valve, the fin and tube evaporator, and the PLC-based smart control system. The electronic expansion valve are used to precisely control the refrigerant flow into the evaporator. This improves the system stability and ensure the optimal performance during the operating conditions. Next, the fin and tube evaporator is responsible for absorbing the heat from the refrigerant space. It provides a large heat transfer surface area, which improves the cooling effect and increase the system efficiency. Lastly is the PLC-based system smart control, which is act as the brain of the system. It continuously monitoring and control the key parameters such as the temperature and the pressure, ensuring that the system operates efficiently and safely. Next, for the table that show the thermodynamic condition at each main point of the cycle, including the pressure and temperature valve. So at the evaporator, the pressure is 200 kPa with a temperature of minus 10.09 degrees Celsius, where heat absorption takes place. After the compression in the low pressure compressor or LP compressor, the pressure increased to 400 kPa with a temperature above 8.91 degrees Celsius. Then, after the high pressure compressor, the pressure further increased to 1400 kPa with a temperature above 52.40 degrees Celsius. At the condenser, the refrigerants remain 1400 kPa and reject heat to the surrounding, bringing the temperature down to around 8.91 degrees Celsius. And finally, at the flash chamber, the refrigerant is separated at 400 kPa at 8.91 degrees Celsius to improve the efficiency and reduce the compressor load. Overall, these results show the thermodynamic cycle of our modified system and demonstrate how pressure and temperature change at each stage to achieve the improved performance and a higher COP. Thank you.
In our design and performance evaluation of the refrigeration system, we first consider the ideal system operate under isentropy assumption. We then determine the enthalpy of refrigerant in evaporator, low pressure stage compressor, condenser, flush chamber, and in the expansion valve. The subcooled liquid at the multi-step flush chamber is analyzed using a constant specific heat approximation, resulting in a reduced enthalpy and a calculated vapor quality after throttling. We calculate the corresponding compression work input of 14.2 kW in low pressure compression and 21.38 kW in high pressure compression. Overall, the total compression work is 28.4 kW, while the refrigeration capacity achieved is 180.52 kW, indicating effective cooling performance of the refrigeration cycle. Under isentropic condition, the ideal COP of the proposed refrigeration cycle with subcooling and injector integration is calculated as 6.356. By accounting for real-world inefficiencies such as compression, heat exchanger, piping, and subcooler losses, the practical COP is reduced to an estimated of 4.388. This demonstrates that the enhanced two-stage vapor compression system significantly outperforms the baseline system, which is COP more than 2.5, leading to improved energy efficiency and reduced operating costs.
Assalamualaikum warahmatullahi wabarakatuh. I'm Syafi bin YUSOFF AD240112. Now we're moving on to the full in-depth calculation for TS and pH diagram together. So there are several components that we have integrated into our advanced refrigeration system, which are multi-stage compressor, which is low pressure compressor, high pressure compressor, intercooler between them, condenser and subcooler, and then followed by expansion valve, flash chamber, and second expansion valve, and then connected finally to the evaporator part. So the values obtained are as follows. For the low pressure compressor, the entropy is going to be 0.9377 kilojoule per kilogram Kelvin. The temperature is negative 10.09 degrees Celsius, and the enthalpy is going to be 244.46 kilojoule per kilogram, and the pressure is going to be 200 kilopascals for the inlet. For the outlet, it's going to be superheated vapor. This is where it changes. And the values are also as stated below. And for the intercooler, for the inlet and outlet, for the intercooler phase is going to be the superheated vapor, and then it's going to be the saturated vapor at the outlet. Now, moving on to the high pressure compressor, which is after the intercooling part. So the phase of the inlet of the high pressure compressor is going to be saturated vapor, and then after it has been compressed for the second time with the higher pressure value, it's going to result in superheated vapor of the refrigerant itself. And then when it passes to condenser or in subcooler, in this case we are treating subcooler and condenser as one component in one shell, because it is definitely not possible for condenser to cool the refrigerant to a point where the expansion valve needs to rise the temperature back again. So we treat them as the same component. So the inlet of the condenser and slash subcooler is going to be the separated vapor after after it loses the heat to the environment or the surroundings, then it will become compressed liquid. And the values are as follows for the enthalpy, entropy, pressure, and temperature. So now we're moving on to the first expansion valve after the condenser and subcooler. It's going to be compressed liquid at the inlet, and the outlet is going to be represented by saturated liquid. And it is an isenthalpic process, meaning the enthalpy doesn't change throughout the valve. And then we move on to the flash chamber. The flash chamber is going to separate both the saturated vapor and liquid at the same time. And since the second expansion valve is connected to the bottom of the flash chamber, then the inlet at the expansion valve is going to be saturated liquid. And after it exits, it becomes saturated liquid vapor mixture. So using the values obtained, these are the TS diagrams for the unmodified and modified refrigeration cycle of our project. The first one is the unmodified version. As we can see, the first horizontal line from the bottom represents the evaporator, and then the second state, which is after the decompression part, represented by the vertical line going upward straight to the superheated region, and then it continues entering the saturation line, becoming saturation liquid vapor mixture, representing the condenser, and followed by the expansion valve, and it recycles back to the evaporator. And the second TS diagram, there are several additional components as you can see right there from the list itself. There are two different compressors, which is low pressure and high pressure compressor, and followed by two expansion valves and condenser and subcooler. As you can see, the difference is that the below graph of the TS diagram, there's two separate compression, and there's a slight slant or gradient difference pointing downward to the left, representing intercooler. It is a very tiny small bit that cannot be seen by naked eyes, since the intercooler does not make a significant difference, but there is some cooling that happens there. So now moving on to the pH diagram for both unmodified and modified version of the refrigeration cycle/system that we have obtained and made together. The first construction of the pH diagram represents the general refrigeration system using the values obtained. The first horizontal bottom line represented by the evaporator, and the slanted line going to the right and above representing the compression, only single compression, and then followed by to the left of the graph, which is represented by condenser and the expansion valve going straight downwards and connected recycled back to the evaporator itself. And for the second pH diagram also, there is two-stage compression. As you can see that there's intercooling, like a small slight line between these two stages of the compression itself. And after the compression is done, there's also condenser and subcooler. Both are considered as one component, and then it passes through the saturated liquid vapor mixture region and goes down into the compressed liquid. And there's two expansion valves, as you can see from the graph, presented by two different arrows and finally connected back to the evaporator itself.
Now we move to discussion. So this slide discuss the overall performance of our proposed refrigeration system. First, the proposed design achieved the coefficient of performance or COP of 4.388, which is significantly higher than the conventional system with a COP of 2.5. This means the system can provide the same cooling effect while consuming the less energy, make it more energy efficient. Now, the main reason of the improvement is the implementation of the two-stage compressor together with the intercooling. So, by dividing the compressor into the two-stage, the compressor requires the less work, while intercooler lower the refrigerant temperature before entering the high-pressure compressor. So, as a result, the compressor power consumption is reduced and the system performance is improved. In addition, the multi-stage subcooler and the plate heat exchanger increase the refrigerant effect by lowering the refrigerant enthalpy before the expansion. So this allows the evaporator to absorb more heat without the increasing of the compression work. Next is the flash chamber and the ejector, further improved by the cycle by separating the flash gas and recovering part of the expansion energy that would normally be waste. So this helps reduce the compressor load and increase the overall thermodynamic efficiency. Lastly, the electronic expansion valve or EEV, and the PLC-based smart control system. So this provides the automatic control of refrigerant flow, pressure, and temperature. So this ensures the stable operation under different cooling loads and improve the system reliability. Overall, although the purpose system is more complex and has a higher initial installation cost, it offers significant advantage in terms of energy efficiency, cooling performance, and long-term operational reliability, making it suitable for industry refrigerant application.
So now let's look at our project milestone for our group. The first week, which is week 9, we start with the analysis of the problem of low COP refrigeration problems that is common within refrigerations and refrigerators that are commonly available. And then Daniel did some literature review and type of refrigeration system selection for this starting of the project itself. And followed by the week 10, which is designed by all of our group members with the new components added into the cycle and do some calculations of refrigeration system design and construct the pH graph and TS graph using Excel. Previously, we have tried to use the AHMAD HYSYS and the WSIM, but we have failed. The first problem that we encountered is that AHMAD HYSYS cannot be downloaded easily. We have to obtain it by the authorized provider. And for the DWSIM, is a bit old school and somewhat a bit difficult for us to understand how it actually functions. And finally, we chose Microsoft Excel as the tutorials are very direct and can be implemented easily. And continued by the week 12, we did some parts, which is refrigerant performance analysis and optimization. So this is the continuation of the TS and patient diagram. And result discussion of refrigerant system and design are discussed by AJMAL to finalize all of our findings and obtain. And then we concluded and tried to finalize all of the documentations by all of our group, and it is done by the week 14. And presentation and video are recorded and uploaded by the last week of our present group project. Overall, for this experiment or research that we have done, in conclusion, this investigation successfully optimized a heavy industrial refrigeration system that is commonly used in multiple industries such as automotives, air conditionings in homes, and many more. We have upgraded a single-stage cycle to a multi-stage cycle by integrating multiple additional stages, which is two-stage compression with intercooler between them, condenser and subcooler, which then furthermore cools down the refrigerant to its compressed liquid, and followed by its first expansion valve, and then flash chamber to separate both saturated vapor and liquid, and followed by the second expansion valve and connected to the evaporator. The modified design drastically reduced specific per input and maximized evaporator capacity, resulting in remarkable 75.5% increase in COP alongside a reduced carbon footprint, meaning this is a good innovation idea that we have proposed. And this highly feasible system successfully balances performance, life cycle, ergonomics, and operability. Since two-stage compressions are cost-effective and does not cause more mechanical failure or damage to the compression itself. Moving forward, the design's efficiency and surface life can be further maximized by utilizing engineering collision solver for parameter sweeps and implementing variable speed drive compressor technologies from industrial leaders like Danfoss and Siemens. Components like the multi-stage compression reduces the work input for the compressor and reduces the temperature of the refrigerant itself. And the second thing is that subcooler and also the valve and the flash chamber that is integrated further cools down the refrigerant to a point where it will increases the refrigerant's capacity to absorb more heat, meaning that it becomes more and more efficient as we have calculated previously. So that is all from us. Thank you.